Welcome to this lesson on momentum in two dimensions. We have been learning about how to apply the momentum principle, which is that the initial momentum plus the impulse equals the final momentum of a system. And so far we've been doing that just in one dimension, where everything is moving along one axis. Today we are going to start working on momentum in two dimensions, where the objects will be moving in both the x and the y directions. Two billiard balls undergo a glancing collision. Before the collision, ball 1 has a velocity of 7.5 meters per second in the positive x direction. So this is the speed and this is the direction of that velocity. And ball 2 is at rest. After the collision, the velocity of ball 1 is 5.4 meters per second. There's the speed at 61 degrees. That's the direction. Find the velocity of ball 2 after the collision. We're going to follow these problem-solving steps in applying the momentum principle. So let's begin by defining a coordinate system and drawing the before and after pictures. So we have objects that are moving along a flat surface. We have two billiard balls. So this is going to be a bird's eye view in our pictures and our coordinate system. So I have my positive y direction and my positive x direction. And then before the collision, what's happening? We have ball 1 with a velocity of 7.5 meters per second in the positive x direction. So here is ball 1, and it is moving this way at 7.5 meters per second, and ball 2 is at rest. And let's think about what we want to label these symbols as. This velocity is the initial velocity for ball 1, but it's all in the horizontal direction. So I'm going to call this the initial x velocity of ball 1 because it's entirely in the x direction. And this is just the initial velocity of ball 2. Okay, then what about what's happening afterwards? So these balls collide. Ball 1 moves off with a speed of 5.4 meters per second at 61 degrees. So afterwards, ball 1, and I'm going to draw this large. You might find it really helpful to draw large diagrams. So I'm realizing when I do that, I'm going to be way out of scale with this. So maybe I'll just make this velocity vector longer so that it'll be a little more to scale. So afterwards, this ball is moving in this direction with a velocity of a speed of 5.4 meters per second, and the angle is 61 degrees. And then because I just drew this and I know we're going to be working in two dimensions, I'm going to go ahead and draw the components of this, the horizontal component and the vertical component. Then ball 2 after the collision, we're not given any specific information about what's happening, but we can actually figure it out. We can figure out some basics of which way it's going. From everyday experience, you probably even know which way it's going. But in case you didn't, let's jump to part 2 and then we'll come back and finish our picture. So define the system. When working with momentum, it can be very valuable to define your system so that it's isolated. If I picked only ball 1, then when ball 1 collides with ball 2, there's going to be a net external force on ball 1, and then I would need to know something about those forces in order to do further calculations. So how could I define my system so that the net external force on the system would probably be 0? Probably by including both objects so that those forces between them are internal forces. So I'm going to define my system to be both balls. And then I'm going to analyze the external forces. So external forces, you can probably think this through now without drawing free body diagrams. We have force of gravity from the Earth, which is not in the system. We have the normal force from for both of them. Normal forces from the surface, which is not in the system. And then we have the forces between the balls. Although those are internal, so I'm not even going to list those because we only need to think about the external forces. Oh, also, what about friction? Okay, so force of gravity and normal forces for each ball, those are going to add up to 0. So I know I don't need to include those. And then friction, I'm going to assume that the force between the balls is so much bigger than the friction force during the collision that this is negligible in comparison to the others. Negligible. So therefore, my sum of my external forces is 0, and that is the definition of an isolated system. So yes, I have an isolated system. If the system is isolated, then I know that the initial momentum, well, no matter what's happening to the system, I know that the initial momentum plus the impulse equals the final momentum. If it's isolated, this is 0, and I know initial momentum vector has to equal the final momentum vector for the system. That helps me think about what's happening. So before the collision, I have, the only momentum is going to be from this velocity vector. So the mass of this ball times this velocity is the initial momentum. Afterwards, one ball is going this way. So it has a momentum that's that way. But when I add the momentum of ball 1 plus the momentum of ball 2, I have to end up with something that's horizontal. Well, the only way this vector could end up adding to something else and getting something horizontal is if the second vector is at a downward angle. So ball 2, I predict, is going to be going in this direction, so that this plus this, right, could equal a horizontal vector. If you kind of sketch that out, this plus this could equal a horizontal. Okay, this then also has components, and it has an angle, and this is the velocity final of ball 2. And before I move forward, I know I'm going to need the horizontal and vertical components. I'm going to go ahead and find those for the information that's given. So for ball 1, we have that this component would be the final velocity in the y direction for ball 2, and this component here would be the final x component of the velocity. I'm sorry, ball 1. This is for ball 1, this is for ball 1. You were probably confused about that. Okay, so cosine is going to give me cosine of 61 degrees will give me this component because cosine is adjacent over hypotenuse. So the adjacent side is VFX1 over the hypotenuse, which is 5.4 meters per second. So VFX1 equals 5.4 times cosine of 61 is 2.62 meters per second. And then I'm going to also find the y component. Maybe I'll do that. I'll just do it over here. Okay, so that's going to come from the sine of the angle. Sine of 61 degrees is the y component of ball 1 over the hypotenuse, 5.4 meters per second. So VFY1 equals 5.4 times the sine of 61, which is 4.72 meters per second. All right, I now have found my horizontal and vertical components of that final velocity for ball 1. So they're now ready to use in my equations. Now for this ball, it also has components. We don't know what they are yet, but this vertical component would be V final y for ball 2, and this x1 would be V final x for ball 2. So we'll put those into our equation as symbols. Okay, we drew a coordinate system, we drew the before and after pictures, we labeled the variables, we analyzed the system. Now we are ready to do the mathematics for the system. And because there's a lot of additional complexity for 2 dimensions, I'm going to draw the bar chart at the end. You can decide when you do these kinds of problems if you want to draw the bar chart at this point or if you want to draw it at the end. So for the mathematics, we're going to write the momentum principle, and we're going to do that for both directions. So what I want to see is all of these steps. So write the momentum principle for each direction. So for the x direction, that is going to be that the initial x momentum plus the impulse in the x direction equals the final x momentum. And then for the y direction, we have the initial momentum in the y direction plus the impulse in the y direction equals the final momentum in the y direction. There we go. That was step 1. Step 2, substitute mass and velocity symbols for non-zero terms. There are 2 objects, so this initial momentum has to be the sum of the momentum of both objects in my system. So going back to my picture, I'm now going to think about each object one at a time. So object 1 is moving. So mass and velocity symbols for non-zero terms. So ball 1 has initial momentum, so I need to include that. So mass of ball 1 times the initial x velocity of ball 1. Then ball 2 is not moving, so I'm just going to go ahead and put the 0. You don't have to do this, but the momentum for ball 2 initially is 0, so these 2 terms make up that. Then the impulse is 0, so that goes with that. Then the final momentum, they're both moving, and they both have an x component. So I'm just going to do everything that's in the x direction in red. So this is in the x direction, this component is in the x direction, and this component is in the x direction. So those are the things that need to go into my x direction equation. So afterwards, I have the mass of ball 1 times the final x velocity of ball 1 plus the mass of ball 2 times the final x velocity of ball 2. And since I'm already thinking about everything in the x direction, I'm going to keep going, and then I'll come back to the y direction. So let me put in now, so we finished step 2, substitute values. So the mass of ball 1, oh, I should have labeled that here, 156 grams, and ball 2, 156 grams. When working with momentum, you can, if you use the same values, the same units for mass on both sides, it doesn't really matter what those units of mass are. So I'm going to leave these in grams. Or actually, I'm going to put them in kilograms, because then it won't get you confused in situations where it doesn't matter. So 0.156 kilograms. The initial x velocity here is 7.5 meters per second. The mass, 0.156 kilograms. Okay, the final x component of the velocity is 2.62. And then mass 2 is the same, 0.156 kilograms. And then the horizontal component of the final velocity, we don't know that, so it just remains as a variable. Okay, take a moment, calculate that out, pause the video, calculate that out, and find out what you get. And we get 4.88. And I'm just keeping an extra value here because I know I'm going to need it. This isn't my actual final answer because this is only the horizontal component of the final velocity. Remember what we're looking for? What we're looking for is this vector, this final velocity. And I should have explained, the basic approach is we find each component and then we combine them together to find what that hypotenuse is and what the angle is. All right, we have finished the x direction. We are now ready for the y direction. So kind of separate things out here. So in the y direction, well, what's going on in the y direction? Initially, ball 1 has no momentum in the y direction. So ball 1 is 0 vertically, and ball 2 has no momentum in the y direction. And there is no impulse in any direction, so that's 0. So what's happening in the y direction afterwards? Going to look at that. So this one has a vertical component of the velocity, so there's going to be a vertical component of the momentum from that, and there's going to be a vertical component of the momentum from ball 2. So those need to be included in my vertical equation. So ball 1. So we have mass of ball 1 times the v final y of ball 1, and then we have mass of ball 2 times v final y of ball 2. So now put in our values. 0 equals 0.156 kilograms. VFY1 was the vertical component of that velocity, 4.72. Same mass for ball 2, and the velocity of ball 2 afterwards we don't know, so it's just a variable. Okay, and now go ahead and do the math, and we get negative 4.72 meters per second. So where are we in solving the problem? We have found the horizontal component of the final velocity of ball 2, and we have found the vertical component of the final velocity of ball 2. But what we're asked for in the problem is to find the velocity of ball 2. So what we need is this hypotenuse vector. We found these components. We need to put them together now to find that final velocity. So I'm going to draw that vector triangle down here. Here's the velocity we're looking for. Here are the components that we have. This component is 4.88 meters per second. This component is negative 4.72 meters per second. And this angle is theta. So we can use the Pythagorean theorem to find the hypotenuse. So putting in each leg of the triangle, we find that the final velocity is 4.88 squared plus negative 4.72 squared. Square root of that is 6.8 meters per second. So that is the magnitude of this vector, but it also has a direction. So if you give this only as your answer, that would not be correct. That is only the speed. So we also need to find the direction. To do that, we can use tangent. Theta is opposite over adjacent. So negative 4.72 meters per second over 4.88 meters per second. So, and it's okay if you don't put the negative here. I usually don't. I usually just deal with this as a triangle with an acute angle, and then I manually put in the sign of that angle afterwards. It's up to you. Just make sure you pay attention to what's going on in the diagram. So we have negative 4.72 divided by 4.88, inverse tangent of that answer, and we get negative 44 degrees. So the actual velocity of the ball is 6.8 meters per second at negative 44 degrees. Okay, the final step is to draw a momentum bar chart for each direction. So here is my x direction, here is my y direction bar chart. So we have the initial x momentum of 1, the initial x momentum of 2, the impulse in the x direction, the final momentum in the x direction for 1, and the final momentum in the x direction for 2. We have the initial y momentum for 1, we have the initial y momentum for 2, we have the y impulse the final y momentum for 1 and the final y momentum for 2. So initially, 1 was moving horizontally, so it had a horizontal momentum, and 2 was not moving at all. There was no impulse. Afterwards, 1 was moving this way with a horizontal component that was positive, and ball 2 also had a horizontal component that was positive. So the initial x component, or the x momentum for ball 1, is just going to be the mass times this number. So 0.156 times 7.5, which is 1.17, and positive, that matches our bar chart. For this one, we need the mass of ball 1 times that horizontal component of the velocity beforehand. So 0.156 is the mass, and then this component of the original, or this component of the final velocity of ball 1 is 2.62. Now, 2.62 was a rounded value, so we need to be aware that what we're putting in here are rounded values. I'm going to put in all these digits though on my bar chart just to help us see that it works out. Okay, and then for ball 2, we have the mass, 0.156, times this component, which was here, 4.88, which is 0.76128. I'm putting a lot of digits so that we don't have rounding errors. So let's add these together now, because what we want to see is that the initial x momentum plus the impulse equaled the final x momentum. That is the accounting that we are doing. So here is the initial x momentum, and these together would be the final. So let's add them together. So this final value, 0.76128 plus 0.40872. Look at that, 1.17. So indeed, we have done the accounting. The books are looking good. What about in the y direction? So initially, object 1 had no momentum in the y direction. Ball 2 had no momentum in the y direction. There was no impulse in the y direction. Afterwards, ball 1, its y component of momentum was its mass times its y velocity. So 0.156 is the mass times the y velocity of 4.72 is 0.73632, and that was positive. 0.73632 kilogram meters per second. And then for ball 2, afterwards, its y component of velocity was negative 4.72. So I'm going to multiply that by the mass to get the y momentum. And you can probably already see what's going to happen. I didn't put the negative in, but it's negative. So negative 0.73632. So we can see that the initial y momentum, which was 0, plus the impulse, which was 0, equals the total final momentum, which adds to 0. The audit is complete, and you are done.